Good afternoon, motivators. Dr. O here, 123 AMP. Lymphatic system. We're going to be covering the lymphatic system, part 1 of our immune system studies. This and next week we'll be covering the lymphatic and immune systems, which are part of the same thing. All right, so we've got a picture of Pac-Man or Ms. Pac-Man, and here we've got the whole concept is that the Pac-Man entity is like a white blood cell. That's right, a leukocyte circulating around, circulate to percolate. It chews up those little ghosts, which are the equivalent of bacteria, of cancer cells, of junk waste products in the body, and we need to remove them and get rid of them so that our body can maintain homeostasis. Here goes. The immune system, here we've got a schematic, an illustration of the lymphatic system in green. These got these little tubes, these small vessels, very microscopic, and every so often you're going to have a swelling in that tube system, and those are the lymph nodes. You have congregations of them throughout the body, and they basically consist of lymphocytes, white blood cells, sitting in these areas and getting ready to take the battlefield to destroy all bad things. When somebody's immune system is fully functioning, we say that they have a degree of resistance. When somebody's immune system is struggling, is suppressed, we call that susceptibility, as in susceptibility to an infection, right? Losing battle versus winning the battle. There are two types of immunity. There's the innate immune response and the adaptive response. The innate response is essentially a combination of things, from your skin as a suit of armor to the white blood cells on the battlefields to circulating chemistry that is designed to purge the body of critters. Then there's the adaptive response, which is when we whisper down the lane and tell all of the rest of the body's cells, in particular its immune system, hey, we've got a bad guy afoot, enemy at the gates, we need to go destroy these guys. So we spread the word, and then everybody knows and is ready to destroy those guys. Here are a bunch of white blood cells circled up around a cancer cell, and they're about to lay the smack down on it. You look at the little green background there, that could be the inside of a lymph node or a lymphatic vessel. The general functions of the lymphatic system, is to drain the fluid that's in between cells. We call that the interstitial fluid. It's also to transport some dietary fats or lipids. So when you break down fats, oils, triglycerides through the diet, the lymphatic system is going to transport some of that. The third function of the lymphatic system is to protect against foreign invaders via the immune response. Check it out. We've got an artery in red, and of course the vein is in blue. We've got some capillaries and venules and blood vessels large and small. Right next to that, the third vessel type, next to the artery and vein, is the lymphatic vessel, pictured in green. So these vessels, they communicate with one another. They all talk to one another. If you break down lymphatic tissue, if you look at it under a microscope, you're going to see a bunch of fiber types that are going to form a lattice work. Imagine like you're looking at a shrub or a bush, and you take a bunch of tennis balls and kids' toys and stuff and stick it into the bush, and those balls, they stay where you place them. Those tennis balls are kind of like the lymphocytes, the white blood cells that are hanging out inside the tissue, this reticular tissue. I know that if you saw that slide of the reticular tissue, you would recognize it. And it's got a bunch of lymphocytes that are sandwiched in there. So here's one, and here's another one. All those little cells, those pink structures in there, are white blood cells. Lymph is going to flow, and it's going to flow from vessels small to large. So the smallest vessels are going to accumulate, and they'll all dump into one large vessel, or a couple large vessels, the right lymphatic duct and the thoracic duct, and these are going to dump into your veins up by the heart and help us get rid of it. Here's a cross section of a lymph node, and you'll see that you see where it dumps into the subclavian veins, the vessels. And this cross section, or a coronal section, I guess, you've got these little areas and these little purple rooms, essentially, inside this green lymph node. All right? And these rooms are where the white blood cells, the lymphocytes go, and they hang out in there. They're like little ready rooms, and when it's time for battle, they leave the room and they go off into the main lymphatic vessel, and they find whatever tissue is being infected, and they destroy. There are some things that facilitate the flow of lymph. We'll call that the flymph, and that is movement, because movement is life, right? So locomotion, using our body, using our muscles, getting that venous return through muscular action, breathing properly will help to facilitate the flow of lymph within the body. And there are also valves, just like in veins. There are these one-way valves that are going to encourage the flow of lymph in one direction. Some lymphatic organs are broken down to primary and secondary, just like blood products. All the formed elements are born in the long bone marrow, the red marrow, and another type of lymphatic origin is going to be found in this yellow structure right in the mediastinal area. That's the thymus. We'll talk about that more in a second. Some secondary lymphatic tissues or organs are the lymph nodes, and you can feel these under your chin and the back of your head. I got this round, kind of tender ball back there. Hey, this is a swollen lymph node. And this is one of the first things you'll learn. One of the signs and symptoms of infection are tender, swollen lymph nodes. So that just means that your body is fighting off an infection. The spleen is also a secondary lymphatic organ, and that can be palpated right in your left upper quadrant below the costal margin, your rib cage there. You hook your fingers underneath your rib cage, you can palpate at least a swollen spleen, which if somebody had trauma to that area or reported pain in that area, you might ultrasound it or palpate. They might report tenderness in there. The thymus, here it is. All right, so it's pictured in yellow here. It's a yellow, soft, triangular-looking organ that sits right on the area of the great vessels, superior aspect of the heart. So it's in the mediastinum, that area. And here you've got a histological slide of the thymus. If you take a look at it under the microscope, you'll see that there are these lighter and darker areas, and within these areas you're going to find T cells. Your T lymphocytes are going to come to the thymus and grow up. All right. Another cross section of a lymph node, both illustrated and in this histology slide. You'll see that we've got cross section of the nodes. They're egg-shaped, roundish, and all these little purple rooms in there, once again, are these ready rooms where the B and T lymphocytes, the two types of lymphocytes, are going to come and grow, hang out, and then they're going to leave through these passageways here. They'll leave the nodes through these vessels and go off to do whatever work. They'll go out on patrol. Here's a picture of the spleen. All those dark areas in there. They call it red pulp and white pulp. The red pulp is essentially where the lymph nodes. The spleen is very vascular. It's got a lot of white blood cells, a lot of lymphatic tissue in it. And once again, it is the largest collection of lymphatic tissue in the body. Red blood cells are going to go to the spleen to die. So once they get worn out after about 120 days, when they get old and shrunken up, They're going to circulate to the spleen, and the spleen is going to break them down and recycle all of their proteins, the iron, etc., etc. Lymphocytes are going to carry things that they chew on, things that they eat up. They're going to carry the spleen, and that'll be recycled as well. This is interesting inside of our gut. This is the cross-section of an intestine. So within the intestinal walls, there are little congregations of this mucosa-associated lymphatic tissue. All right. They're otherwise known as Peyer's patches, P-E-Y-E-R-S. Peyer's patches are this right here, these collections of lymphocytes. They're all jammed in there at the ready, so that if a bacteria or a parasite or a cancer cell starts to act up in the gut, these lymphocytes can spring into action. Lymphatic tissue development. So lymphocytes, just like all formed elements, are born and raised in the red bone marrow. They are produced from a parent cell, a stem cell. In other words, a blank slate. And that blank slate is going to differentiate, and it's going to ultimately become one of the white blood cells, in this case, a lymphocyte. Let's talk about innate immunity. Innate means our ability, an ability that we're born with to thwart disease, to get rid of infection. All right. So there are physical things that help us maintain our immunity. The first barrier between us and disease, let's say bacterial disease and infection, would be the skin. That's our suit of armor. Then we have a body chemistry where chemistry is circulating throughout our body, and if there is signs or symptoms of inflammation, a bacterial invasion, let's say, those chemicals will proliferate, and they will help a series of events to happen to maybe produce a fever, and that fever will produce some inflammation, and that inflammation is essentially the body healing itself, body fighting a battle, winning the battle, and then maintaining homeostasis. Here's a picture of the stratified squamous epithelium in the skin. Mucous membranes they're wet skin, essentially. Stratified squamous epithelium inside your cheek, inside your mouth, your gums, your vagina. These are all areas where the skin is wet, and so those are called mucous membranes instead of epithelium, like skin. Antimicrobial substances that circulate within our body. A big one is interferon. So you'll hear some folks, if they have a suppressed immune system, these chemicals called interferons will start to circulate naturally. If somebody has continued suppressed immune system, if they're immunocompromised, all right, write that down. That means that they have a chronically suppressed immune system. When a patient is immunocompromised, we might administer interferon. We might inject them with that, put them on an interferon drip, so that we can get these antimicrobial substances circulating and kill all bad guys. The complement system is a series of chemicals that are going to be like poison to microbes. There are other specific proteins that have antimicrobial properties as well. Think of it as like antimicrobial soap or an antibiotic. These antibiotics that chemically circulate throughout the body and help resist disease. Here's a natural killer cell. Okay, there's a type of white blood cell that it's particularly ruthless against pathogens. So it's like a Pac-Man that goes around gobbling up junk. And their method of fighting is to engulf their phagocytes. So they eat critters. You might be interested to know how inflammation and fever can actually be a good thing and help us fight infections. So here's a natural killer cell eating up a bacteria. Once it's digesting the bacteria, it'll release this chemical called an interleukin, abbreviated IL. The interleukins will communicate to the nervous system here in the hypothalamus, and the hypothalamus will produce a fever, an elevated temperature. This fever is going to be useful. By elevating our temperature, it's going to directly help us destroy some bacteria which can't tolerate that much heat above normal body temperature. And the increased temperature also makes it possible for interferons to be more effective. All the chemical reactions in the body are going to happen more quickly when the body is warmer, when there's a fever. And so that'll help clean up the areas, produce inflammation that's ultimately going to wage a battle against the bacterial invasion and move on down the road. The adaptive immunity. This is when a white blood cell, specifically a B lymphocyte, a type of lymphocyte, that is going to encounter an antigen. An antigen is any sort of foreign invader in the body. So let's say the white blood cell encounters a bacteria. The white blood cell will never forget that encounter and will go off and tell all the other white blood cells, be on the lookout for this microbe because they're around. And so it's not just the one bacteria, the one part of the immune cell, the one immune cell that knows now. Everybody knows, and they're on the lookout. Here's how it happens. Immunocompetence is when B and T cells have been seasoned in battle. They've gobbled up plenty of bacteria, so they're like old veterans of war. They know, they're more comfortable, and they know how to maneuver and to ultimately win the battle. In the thymus, remember we said the T lymphocytes or the T cells, that's where they go to grow up. So once the lymphocyte is produced in the bone marrow, it's going to migrate to the thymus, and in the thymus, those cells are going to grow big and strong, only to go out and destroy foreign invaders ruthlessly. Two types of adaptive immunity. There's cell-mediated immunity and antibody-mediated immunity. Okay? The antibody-mediated immunity is where certain lymphocytes are going to produce these antibodies, which is like an antidote against poison, right? So once these antibodies are circulating throughout the body, it's like we're able to identify that bacteria when it comes in. So the antibody count is up. We'll be able to destroy any of the invaders. Cell-mediated immunity happens with cytotoxic T cells, and this is a cool graphic. You can see a white blood cell coming over, and what it does is it punches holes in a bacteria, and then it lets all of its guts spill out all over. All right, it's kind of like you blow up a balloon, and then you let the air out of the balloon, and it flies all over. That's the effect that these cytotoxic T cells have over bacteria. They'll go inject them with this poison, which destroys them. Here's an example of antibody-mediated immunity, where B lymphocytes are going to transform into what are called plasma cells, and plasma cells are going to increase and secrete antibodies. When a lymphocyte grows up and increases in number, they call that proliferation, and what they do is they form clones. So let's say we have a really capable warrior white blood cell. That white blood cell, is going to be able to clone itself, split up into 1 million warriors of the same strength and with the same knowledge carrying the specific antibodies. And so it's battle ready. It really is like the Clone Wars. They'll be able to, in that way, increase their numbers and destroy all foreign invaders. Effector cells and memory cells are the two types of T cell, or lymphocytes rather. So the effector cells are actually going to be the ones go out and destroy the antigens. The memory cells are going to be, they're going to like talk shit. They're going to go out and they're going to tell everybody else that the battle is about to begin. And here's a bacteria that has been, it's got its antigen receptor in the plasma membrane. Antigens are defined as any chemical substance that is recognized as foreign by the immune system. Receptors are very specific. They're very diverse. There's a lot of different types of them. All the cells in the body, we need to be able to differentiate between good and bad cells. So we don't want our immune system to destroy, to attack our skin or our heart or our liver. We want our own body's cells to be unscathed in these battles. We only want to destroy the bacteria and the parasites and cancer cells, right? The bad stuff. So there's something called a self-antigen. And this is like if we were all on the team, we're all in the Philadelphia Eagles, we would have our Eagles jerseys on. Well, if you're on the Eagles, you're not going to be tackling the Eagles. You're going to be attacking the Giants or the Seahawks or whoever, the other team. So self-antigens prevent us from attacking our own teammates. Cytokines are an example. These are chemicals that are small protein structures, and they are very important with regulating the immune response. These are chemicals that are circulating around that help the immune system respond. Here's a sequence of the cell-mediated immunity, just to break it down because there's a lot of information. Definitely know this slide. There's the activation of a T cell. It's getting ready. It identifies that there's a antigen on the field, a player on the field with a Giants jersey, and we're all Eagles. That T lymphocyte is then going to bind with that molecule, with the antigen, on the surface of the antigen. Chemicals are going to be circulated and released. The clone wars are going to begin. The T cells are going to destroy the bacteria, and the B cells are going to produce antibodies. Everybody goes home. Antibody-mediated immunity. It's going to happen where the lymphocytes secrete antibodies, and antibodies are substances that are going to neutralize the antigen. They're going to immobilize it, and they're going to cause those, let's say, bacteria to stick together. We call that agglutination. Antibodies are also going to communicate to other white blood cells to, hey, come and eat this guy, kick this guy's ass over here. And antibodies will also activate the complement system, which is chemical. There are different types of antibodies. They're called immunoglobulins, IgG, IgA, IgM, IgD, IgE, are some examples. I'm not going to expect you to know the specific functions of those. The complement system, here's an example of that, is a group of proteins that are going to complement, quote unquote, the immune responses and help clear all antigens from the body. The concept of immunization. Okay, it's been around for a long time. It's made possible a significant reduction in chronic disease throughout the world. Afflictions such as smallpox, polio have been rendered almost non-existent due to the advent of vaccines. There are many others. We just came out with a vaccine for HIV, I believe. So certain microbes are going to be more subject to immunization than others. Essentially, immunization is a matter of the antibody-mediated immunity, where the B and T cells are going to be artificially activated, let's say by, we're going to administer the smallpox vaccine. Well, we are, without exposing ourselves to the disease in full, we are going to be injected with a very small amount of an inactive form of the smallpox antigen, so that our body is ready should we ever, God forbid, encounter the smallpox disease. Our body would have a natural defense against it. It's been proven to be effective. It's important to reflect on our nervous system studies and consider how stress is going to reduce our immunity. We call that the general adaptation syndrome. Remember Hans Selye? He studied rats, studied rodents, tortured them, and then dissected them and found that their immune systems were suffering. So there's a link between our mind and our endocrine system, our hormones, and our immune, and the strength of our immune system. If you're stressed out chronically, you're gonna be more subject to disease. That was a lot. Take it all in. As we get older, our immune system is not, the structure and function of our immune system is not what it once was. All right? So therefore we become less able to adapt and tolerate situations where we become infected, or in the case of cancer, our strength is not up to par in some circumstances. Some things that we can do to ensure a strong immune system as we grow older is to get plenty of fresh air, sound nutrition, exercise, manage our stress, and maintain a healthy cardiovascular system so that everything can flow and all the warriors can take the battlefield. Thank you and have a nice day.